All right. Good evening, everyone. So, this is week two, right? So, Let me reiterate this once again. So, it becomes extremely cumbersome for me to admit each and every one of you. I mean, the time is 4, right? So, please try to stick to this timing to join the session. After that, it becomes very difficult for me to keep admitting everyone one by one. So, please try to stick to the timing. Try to be present here before. Oh, sorry. Yeah. Hello. Hi. Yeah. Good evening. So I was saying that please try to be on time. Okay. Don't try. Miss. Don't come late. I mean, it becomes extremely difficult for me to keep admitting every one of you. Okay. So after the timing, it's the actual time is 4. So try to stick to that time. Don't be late. That is what I'm saying. Please try to be present before 4 so that we can start the session on time. Okay. Fine. Uh, I was just seeing a question in the chat box. About the recordings, I did post my last week's lecture on YouTube, and unfortunately, the job of sharing that this thing video with all of you is of NPTEL, right? But they have not posted it yet. But anyway, I did share the link in the chat box. Okay. So in the Swayam portal, there is a chat box. Yeah, so I did share the link of YouTube of my YouTube recording on the chat box in Swayam portal. Okay, so if you want, you can access it from there. I will be posting this week's YouTube link also on the same chat box only. I hope that the management, I mean they are swift in their action and they recognize this problem, and I mailed them actually about this problem. They will be uh, most probably sharing it with you. I mean in due time. So, but for time being, I have posted it in the chat box, so you can access it from there. Okay, cool. I will post it in the chat box again after this week's this thing. Fine. So before starting, is this visible? I hope it is visible. Okay.
Yes, sir.
Yeah. Cool. Yeah. Again, this is what? 1 second. Yeah. So this is week 2, right? So sorry, I'm getting disturbed again and again by the people who are joining in late. Please try to stick to the time. Don't be late. Anyway, this is analog IC design, an NPTEL course, and it is taken by the instructor Dr. Sankar Aniruddhan. He is from the Department of Electrical Engineering at IIT Madras. Myself, I am the tutor for this course. I am holding these discussion sessions. So this is week 2. My name is Mayank Anupam, and I am a PhD student and PMRF scholar here. Okay, so I am from the Department of Electrical Engineering at IIT Kanpur. Okay, so that's the introduction.
Yes,
Before
sir. Yellow.
before moving on to this week's content, let me ask: do anyone have any problem in the last week's? I mean, week one's content? Any issue? If someone has some doubt, they can unmute themselves and ask me if they have any doubt in the in week one's content. Okay, so if there is nothing, then I will be moving forward. Cool. So in this in this session, I will be discussing about week 2. Okay. So I know that you also have to attempt week 3 assignment in this week. So I will also be covering some portion of that, but I will not be covering it in detail. I'll just be covering the topics which you will need to to attempt the assignment. Okay. I'll be discussing a sample question which will help you in answering the questions of your assignment, but the detailed discussion of week three's content will be there in next week's session. Okay, so this week this session here is primarily focused on week 2. Okay, so I'll be starting with week two's content here. Okay, so yeah, so in week 2, what did we learn? We learned about negative feedback, right? Negative feedback with delay, isn't it? So I'll be quickly going through this concept once more so that we are on the same page. So we know this, right? That in any system, in any negative feedback system, what do? We have a reference signal, okay, and we have a feedback signal, and there is a sensor. There is a feedback path here. There is a feedback path here, and there is this forward path here, and then this is the condition here. Okay, this is a feedback system. Okay, so if there is a if the problem with feedback is that this is a closed loop system, right? It's closed loop feedback system. Now the problem with this circuit is that if there is a delay here somewhere, anywhere in the circuit, if there is a delay, then basically this will introduce this has a potential of becoming. One second. So there is something in the chat. Yeah, so as I was saying, if there is a delay somewhere in the system, anywhere in the system, then this has the potential of making the whole system unstable, whole closed loop system unstable. And the intuition behind this is that, let's say again, we go back to the classic motor driving example, right? Bike driving example. So you remember that if you're trying to drive a bike, and let's say your speedometer gets stuck. Okay, uh, let's say your speedometer is working, but it has some delay. Speedometer has some delay. Okay, so because of this delay, you will not be getting the information about the instantaneous speed at that particular instant itself. You will get the speed at a later time, right? And let's say you were accelerating, right? Let's say you have reached your desired speed of 40 kmph, but still speedometer shows that you have still not reached it. You are still at 39 kmph only. So in that scenario, what will happen is that you will keep accelerating, right? You will keep accelerating, and it may so happen that you can become your speed can never converge, right? You may never be able to reach your speed of 40 kmph. You may keep on going back and forth, and the whole this thing, your speed controlling system becomes unstable, right? So that is the logic behind delay. So delay in a system, like if I bring this figure again here, sorry. I bring this figure here. Then basically, let's say there is a delay here, okay, and this is your feedback system. If there is a delay here, right, then this delay can cause the whole system to become unstable. So that is the whole idea of delay in negative feedback, right? So delay in negative feedback can be very hazardous, okay, and it is something which we do not desire at all, right? Okay, so this is what was covered in the week mainly, right? So the whole discussion was about delay in a negative feedback loop. Okay. So for like I will not be covering the maths that was covered in the lecture, so you can go through that on your own in your own time. So it was covered in pretty details, right? So I'll not be covering that again. I'll just be discussing some intuition, okay, about what happens because of the delay and all. A lot of things were discussed in the session in the lectures, but I'll be covering some different point of views. Okay, so this was about ideal delay. So if there is an ideal delay in the system, ideal delay is what? Let's say if you have a signal x of t, okay, and if this passes through an ideal delay td, then what do you get at the output? You get x t minus td, isn't it? This is what you get, correct? So this is what you get when you pass your system to through an ideal delay, okay, through your signal through an ideal delay. All the whole signal is getting delayed by the time, right? So there is so this is what is ideal delay. Now in a circuit, okay, yeah, so in a general in general circuits, okay, so you will not face this ideal delay situation. General circuits, you may or may not encounter ideal delay. Okay, so what you will have in a general circuit is that you will have this elements, memory elements, right? You have this memory elements in your circuit, which are capacitors and inductors. These are the two memory elements which you have in your circuit. These two memory elements, as the name suggests, they are very good at storing past values, right? And it so happens that they are also because of this particular phenomenon that they show, they also give rise to some kind of delay. Now this delay is not ideal, right? So you all know that a capacitor here, the voltage across it, right, it does not change instantaneously, right? It cannot change instantaneously unless you have a infinite amount of current, okay? So if there is a finite amount of current, the voltage across this capacitor here cannot change instantaneously. It changes gradually. Now voltage across a capacitor changing gradually means what? Let's say you are driving it with some current source, okay, this capacitor, and let's say your current source has made a sudden jump. Let's say this was 0 ampere and suddenly it became 1 ampere here, but the voltage across this capacitor, it will not jump suddenly. It will start ramping, right? This voltage here, it will show this kind of behavior, correct? So you see this voltage here is not jumping suddenly. It should have jumped, but it does not jump. So I mean, this is what you understand qualitatively by saying that this capacitor here offers some delay in the overall circuit. Capacitor does not give an ideal delay, but it gives it delays the overall response over a period of time. Okay, this is what it means when we say that a capacitor is not an ideal delay element, but it does introduce a delay. Okay, fine. So in your circuits, in the circuits that we will be seeing, the delay elements, yeah, so in the circuits that we will be seeing delay arises from capacitors and inductors. Okay, so most of the times we will not be bothering about inductors because inductors end up taking a lot of space on ICs, and inductors are not used unless they are I mean they are absolutely required. Most of the times people go with capacitors. So capacitors are the thing which will be present on an IC, and they will be introducing some delay. Okay, fine. So
Sir,
yeah,
ideal delay और non ideal delay एक और नहीं समझ में आया difference.
okay, so yeah, okay, fine. So you see, this is an ideal delay, right? This is an ideal delay block, correct?
Yes sir. Yes sir.
Yeah, but what
Ah,
what do I mean by non-ideal is that, you remember capacitors behavior is how do I explain it? Okay, fine. Let's say this is a voltage source. Okay, now there is a resistor here and there is a capacitor here. Okay,
yes sir.
you know this is an RC circuit, right? If you
Yes.
give a step voltage at this input,
Yes.
at the input, then what happens to this voltage here?
This will increase gradually.
Correct. So let's say this is your input voltage. This is your input voltage. Okay,
Yes sir.
V in, and yeah. So what will be the output voltage here? Output voltage will
Output.
be like
Yes.
this, isn't it?
Yes. Yes
You
sir.
see that ideally what you would have wanted, if this would have been a resistor divider, let's say it would have been a resistor divider. Okay,
Yes sir.
so what would have been the response here? If the input was like this, the output would have been a sudden jump here and then like this, isn't it?
Yes sir.
This would have been the output. But in this case, what happens to the output? It is it rises gradually and then becomes equal to the V input after infinite time, right? But let's say we are only considered about, let's say, 99% accuracy. Okay, then that happens after this much of time, isn't it?
Yes.
So you can say in a way, you can approximate in a way that the whole system, the whole your whole output signal is like shifted, right? You can say that it is shifted. Your signal is actually appearing after this time, isn't it? You can say like that, right?
Yes sir.
So this is what I'm saying. What I mean by a non-ideal delay. There is a delay here also, but this delay only manifests itself after a very long time. So after a very long time, you will, when you compare these two waveforms of this V out and this V in, then you will say that okay, so V out is slightly shifted with respect to V in, right? That you can
Yes
say.
sir.
So that is what I mean when I say that it is a non-ideal delay. Okay.
Okay sir.
So this capacitor
Sir,
here, yeah,
okay, sir, please, you can complete, and after that, I will ask my doubt.
yeah, I have completed. You can say what you will
Okay.
say.
Sir, for the week 3 content, that is basically based upon the parasitic poles and all,
Yeah.
parasitic poles zeros.
Yes.
Like for the week 1 and week 2 questions, we refer to Sergio Francisco book
Yeah.
to solve the questions.
Yes.
Which book can we refer for the week 3 content?
Uh, week three. So week three content you can refer from. I think in the in Sergio Franco book also there is a part on negative feedback. You can refer there. It's okay. This is
Okay,
pretty
it
standard
deals.
stuff. This is the week three content was mainly about Nyquist criteria and all. It's pretty standard control system stuff. Okay, you can get it in any book, any book, any book on analog IC design or any book on control system will have this thing covered. So in Sergio Franco there will be definitely, there is a portion where they discuss about negative feedback and stability. Okay, from there you can refer the concepts. Okay.
Okay, sir. So the questions on in the control system book will also help out in
Yes.
solving the
Yes.
questions of week
Yes.
3.
Yes.
Okay,
Yes.
sir.
Yes. Fine.
Thank you, sir.
Yeah. Yeah. Welcome. Cool. So this is what is a non-ideal delay. More precisely, this capacitor here, the capacitor and inductor, they do not result in a time delay, but more precisely, they introduce a phase delay. Okay, they introduce a phase delay. These capacitors and inductors, they introduce phase delay. Okay, so you remember that uh, what is the impedance of a capacitor? Capacitor is like this, right? So what is its impedance? Impedance is 1 over j
One
omega
by
c, right? Correct. So it is 1 by j omega c. Yes. So it is 1 over j omega c. So what is the phase of this guy here? Impedance. It's minus 90 degrees, isn't it? Yeah. So it is minus 90-degree phase. Correct. So it means what? It means that if you apply a current across a capacitor and try to observe the voltage, then the voltage V out will be 90-degree phase delayed with respect to your input current, isn't it? So precise, if you want to say more precisely, the capacitors, they introduce phase delay, not time delay. Okay. So but I will be explaining now what I mean, what I am going to say next. So let's say this is I in of omega. Okay. So are you people comfortable with this uh, Fourier transform and things like that?
Yes, sir.
yes, sir.
Yeah, I guess you will be
Yes, sir.
comfortable. Fine. So I'll be moving. So what I'm going to say is that let's say this is yeah, let's say this is I in of omega. This is the current. Okay, and this is V out. This will be some omega only. Okay. Now you know that I in of omega multiplied by 1 over j omega c is equal to V out of omega, right? Correct. Now let's say I in of omega is equal to e to the power j omega of t. Okay, I am using a complex sinusoidal current source. Okay, this is a 1 into e to the power j omega t. Yeah, so okay, fine. So what I was saying, yeah. So let's say this is let's say I'm not let's not make our life comfort. Let's not make our life difficult. Let's say this I in of omega is actually equal to, let's say, some sine of, or let's say some cos of omega t. Okay. So when this does pass through this capacitor here, what will be the voltage V out? V out is equal to cos of omega t uh, time divided by omega c, right? Sorry. Yeah, divided by omega c, and there will be a phase shift, right? And that will be equal to minus 90 degrees, isn't it? This is V out. Correct. So if you see in the time domain, let's say this is your input signal, input I in, which was a cos. So this is like this. Okay. Okay. So your this is your input, oh, by the way. This is your I in. So your output here will be 90 degree phase shifted, which will simply become sinusoid, isn't it? So this is like this. This is your output. Okay. So you can see that here it is clearly seen that this is delayed, right? Your input was cos here, and your output has become sine, and this is delayed. So precisely if we say, then this is a 90-degree phase shift. This here is a 90-degree phase shift. But this 90-degree phase shift can also be viewed as some kind of delay in the system, right? There, the input is a cosine of omega t, but your output is it is a sine of omega t, right? So it is slightly shifted, it is slightly delayed. Okay, so this is what happens when you have parasitic capacitors and parasitic capacitances in your circuit, parasitic poles in your circuit. This is precisely what happens. They introduce some phase delay, and because of the phase delay, you have some kind of time delay. Okay, fine. So this negative feedback with delay is a very dangerous situation. Delay is nothing, not something which is desired. Ideally, what do you want? You want your feedback signal to come instantaneously to the comparator. Okay, so that I mean, this is the feedback here, right? This signal should come instantaneously to this comparator here, so that the comparison happens almost instantaneously. Okay, and so that you get the correct comparison here, and then the correct error signal here is generated, so that the controller takes the right decision. Fine. Okay, so after that, what did you have? We also learned about this Nyquist criteria, isn't it? But before that, let's quickly revise loop gain. Okay, so let me take this same example as, yeah.
Sir, what is the best time delay where the system could be stable?
Yeah, so it
Is
was
there any?
discussed, right? I mean, it was
Okay.
discussed in the lecture. So
Yeah.
delay was equal to 1 over, sorry, not 1 over, pi by 2 times
Yeah, it
normalization
is.
of k by omega u. So this was what was discussed, isn't it?
Yeah, it's K can be anything of the system, or
No, k
if
is
it is thousand.
k is
Uh,
what? K is this, right? So let's say this is your vref, and this is the adder here, and then you have this thing, omega u here, sorry, 1 by omega integrated 1 by omega u, or
yeah, K is nothing but the voltage gain.
correct.
Yeah. Okay. Yeah.
1 second. And here you have this resistor divider, right? And this was k minus 1 by
And
r, and this is r.
yeah, and
Correct.
V out by K would be the ratio. Okay.
Right.
Got it.
This is what was given in the lectures, right?
Yes. Yes. Yes.
Correct.
Yeah.
So fine. So this is the system which we have been which sir has been discussing in the lectures. Correct. So yeah. So what is meant by loop gain in this system? So can anyone answer that question? What is meant by loop gain in this?
Transfer function.
Yeah. What is loop gain?
Loop gain, it formula we have to tell, or how to find out the
Yeah. How
loop
to
gain.
find out? How to find out?
Okay, so then V in should be grounded, and
Okay.
okay, and what are the V reference? What is the negative one is there? Na? So that there we have, sorry, W omega U by S. There we have to give the input,
Here at
test
this
input,
point.
and yeah, test input, and
Okay.
just check the output at the feedback. When the feedback is coming, then that beta K minus 1 are that point, junction point.
Okay. At this point, we have to see the output,
We have
right?
to test it out.
Okay. Yeah. Fine. So
So
this
that
is
will
what it
tell
is.
in,
Yes.
yeah.
So this is the we, let's call it V return. Okay. So this is what is done in the loop gain exactly. So what do we do here? Loop gain is what? Loop gain is actually equal to omega u by ks, right? That's all. Here the loop gain is omega u over ks. Fine. So
Sir,
yeah,
uh, sir, why don't we consider negative sign? Because it's a gain,
yeah.
and we
You can
consider.
put negative sign here. Doesn't matter. I mean, we are talking about loop gain. It is implicitly understood that there is a negative sign. That is why I have omitted it here. Okay,
Yes, sir.
yeah, it doesn't matter. I mean, as long as you know
Uh,
what you're doing.
yeah, it should have been either omega into k by s, right? Because k is the gain.
No, it is not k. It is divided by k here, isn't it?
Yeah, yeah, it's divided by k. But I had this question like k is then gain of the system. Then it should multiply with the gain factor,
No, I mean I have
isn't it?
put an attenuation here, isn't it? For this particular system, what is the loop gain? That is what I'm asking. So
Okay.
in the feedback, I have attenuated the feedback signal by k and then fed it back to the signal
Okay,
output
fine,
here.
got it. So the that feedback network would be v out by k.
Yeah,
That's why it
this
is
is
coming.
V out by k,
Okay,
right? It is up to you. Feedback network design is up to you. You can also amplify the input, output, and then feed it back. You can, if you want, you can attenuate it as we are doing it here. Okay,
okay, mhm,
fine.
got
So
it.
this is the loop gain. Okay, now fine. Now in this loop gain, uh, can someone tell me what was meant by this one unity gain frequency?
omega u by k,
So what is meant by unity gain frequency?
where the magnitude of the loop gain becomes 1.
Correct. So if let's evaluate loop gain at j omega, right? And then let's find its magnitude. So this will be omega u over k times j omega and whole magnitude. That will be omega u divided by k times omega, right? And when this equals 1, at that time we say that this guy omega here will be omega u loop, right? Which is just a shorthand for saying that we have this is the unity gain frequency, isn't it? So what is omega u loop? This is equal to omega u over k, correct? Fine. Now let's evaluate the system with some delay. Okay, so as was discussed in the class also. So if your system omega u over s into s plus p1, if this is your system, so what will happen in this case? I mean, what is the loop gain again?
Just the pole gets multiplied.
Yeah, correct. So it is again the same thing, just that there will be a pole here, correct? Again here also, if we have to find the the unity gain frequency, isn't it? And what is so special about this unity gain frequency? Why am I stressing at this term again and again? What is so special about this unity gain frequency? Can someone say?
Uh,
where
we-
the gain becomes zero.
Yeah, no, gain does not become 0. Gain becomes 1.
so basically from here
Is
we
the
can
pole
find
of the
the
system?
PS margin from.
Okay, so everyone is saying something, but see, you see this negative feedback. Remember that the whole concept of negative feedback works. The whole negative feedback works on the principle that something is coming from the output side and it is fed back to the input, right? There is some information of the output which is coming back to the input, isn't it? Right? And then basically this is basically given back to the input, and then you are processing it further in the error block here, right? So the loop gain, what does it mean? It means that inside the loop, if at any point, let's say at this point, you have applied some signal, what part of this signal comes back again here, right? As we return, right? This is what is loop gain, isn't it? There is some part of this signal will be amplified and then come back, right? At this will return back here, as we return, isn't it? This is the whole concept of loop gain. Now why is loop gain so important? I mean, what is so special about loop gain? It just says it is just a quantification of how much of how accurately your feedback is working. Okay, so basically, what I mean by saying is that you see, if you apply something here, and if the feedback is very strong, okay, if your feedback is very strong, then what happens? Something which you apply here, in return of that, a very powerful, powerful amplified signal will come to oppose that, isn't it? If the feedback is very powerful, okay. But if the feedback is not very powerful, then then the returning voltage here will not be very strong. It will be very diminished. Okay, when will you say that the feedback is not working? When will you say that the feedback is not working at all? When no signal is coming back, isn't it? When you apply something here and nothing is coming back here, then you say that the feedback is not working, isn't it? So it is just like removing this everything here. Okay, now if you apply something here at this point, nothing will come back here, right? Because you have removed the whole network, nothing will come back. So in the same lines, even if you have connected it here, and let's say after certain frequency, if you apply something here and nothing come back here, I mean, if something is coming back, it is extremely small, it is just very small in magnitude, then you say that the feedback is not working. Okay, so the whole idea of this unity gain frequency is that it is the point where the loop gain becomes equal to 1. I mean, if you apply something at the input, exactly same amount of magnitude is coming back. Okay, and that is the point where you see that after this feedback is not working at all, because even if you apply something at the input, the return voltage is which is coming back is even smaller than that. Ideally, what do you want? You want your gain, loop gain, to be very high, isn't it? It means that when you apply something at the input, when you apply something at this input, the returning voltage here should be extremely large in magnitude, isn't it, compared to this input. And then you say that the feedback is very powerful. But if it happens that your feedback signal is exactly equal in magnitude to the input, then basically you say that you have the frequency at which this is happening is basically your unity gain frequency. And you also mean and from this you can also infer that after this the feedback is not working effectively. Okay, even at this frequency of unity gain frequency, the feedback is very small. Feedback is just equal to the same input voltage that you have given. Okay, so is that clear for everyone?
Yes, yeah.
Okay.
Hello,
Yeah.
sir. You said that the feedback will be weakened, right? When
Yeah.
we,
Correct.
so weakened in the sense because we are actually we are attenuating our output signal, right?
No,
So
no. This is okay. 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 So
yeah, we
this,
are attenuating by k, right?
yeah, we are attenuating
So
it by k. Yes.
so that means that we are intentionally weakening it, and that weakening it depends upon the how much feedback factor that we are applied.
Okay, so I understand your question. So see, we are weakening it here. Yes, you are right. We are weakening it here, but we are amplifying it here, right? This is an integrator. Integrator has ideally an infinite gain at DC, and also this block here, its job is to simply amplify everything that is coming here at its input. Okay, so this amplification is happening here, and yes, you are right. We are attenuating it here, but as long as the amplification factor is much larger than the attenuation factor, the overall loop that will have a very large gain. Okay.
Okay, so that means that sir, our unity that UGB is the maximum frequency where the signals will be allowed, right?
No, it
That
is
is
the
the
maximum frequency till which you can say in some manner. Okay, it is not exactly. It will not be very correct, but you can say that in some manner your feedback is working. Okay. After that, your feedback is not working. You can say in that manner. It's not a very politically correct statement, but yeah. So your feedback is working till that frequency, and after it is not working. You can say.
yeah, yeah. Thank you.
Yeah. Welcome. So fine. So this is clear, right? So now moving forward. So this is what unity gain frequency actually means. Fine. Now, yeah. So this loop gain here, we already have discussed this, that because of these parasitic poles, the system has a tendency to become unstable, right? This overall negative feedback has a
सर
tendency. Yeah.
सर जो डीसी गेन होता है सर उसकी यूनिट क्या होती है व्हाट इज द
Uh,
यूनिट ऑफ डीसी गेन
DC gain is unitless, right? Gain is unitless. Gain voltage to voltage gain is unitless, right? It is V by V. It is unitless.
we have a question in our assignment regarding that in which we have asked
I'm not able
to
to hear.
find.
I'm not able to hear you. Please.
Hello.
Yeah. Hello.
I will write my question in chat box.
Okay, you write your question in chat box. I'll be answering that. Fine. So moving on.
Sir,
Yeah.
sir, so you said that it will be unstable. That means that at UGB our phase margin will be zero, right?
Correct.
So suppose if by designing a system and it is a suppose let us say that our loop gain has a second order system whatever you have written like omega u by s into
Hmm.
s plus 1.
Yes.
So for that the UGB will be square root something like that, and it depends upon the system, right? System also, right? How many poles also present like that.
Yeah. I mean, precisely saying this is not a unstable system. With two poles, you cannot have an unstable system. Okay, so I was just saying, my assertion was that if you have poles in your system, in your negative feedback system, there is a tendency for the system to become unstable. For a second order system, a system is unconditionally stable. Okay, because it can never reach 180-degree phase shift. Right, loop gain phase margin will never reach 0 degree. It will reach 0 degree only at very high frequencies, infinite frequencies. Okay, so technically speaking, your this second order system is unconditionally stable. But let's say if this becomes a third order system, right, then it has a possibility that it will become unstable, right? So all I was saying is that if you have some poles in the system, then the system has a tendency to become unstable. Okay, now if the system becomes unstable, okay, so answering that guy's question who asked about DC gain. So you see, DC gain is unitless, right? And dB is not a unit. I mean, it is just a way of representing. dB is nothing but 20 log of something. Okay, 20 log of a unitless quantity. That is what is dB. So there is a unitless quantity here. So if you want to find out, let's say if you have a 60 dB, what does it means? It means that 60 dB will be equal to what? 20 times log with the base 10. Okay, and there will be this gain. Okay, and what will be this AB? This will be 3, 10 to the power 3, right? This is basically 1000. So your gain is 1000 here. Okay, 60 dB means this is what is dB. Something in dB is actually 20 log to the base 10 of that quantity, for which you find the dB this thing. Okay, yeah, fine. So fine. So I was saying that this loop gain, it is it can become unstable. Sorry, not loop gain. Closed loop system can become unstable if there are parasitic poles and zeros in the system. Okay, and so basically in the lectures a lot of examples were given, right? And a lot of calculations were shown, were also done in order to show that how the system becomes unstable. So I'll not be covering that here again. I'll not be summarizing that. So my idea is here is to just focus on this Nyquist criteria. Okay, because this is where this is something which you need to know, and this is also important for your assignments. So what does Nyquist criteria say? So anyone, what is Nyquist criteria? Anyone?
So it's basically based upon number of poles that are present in the right half plane will be equal to the number of times the circle encloses minus 1 comma 0 point.
Correct. And you also forgot a very important this thing in that. It is
Clockwise
actually
direction.
correct. It is actually clockwise direction encirclement. If you have
Yes, sir.
anti-clockwise direction encirclements, nothing happens. Okay.
Okay, sir.
So cool. So this is, sorry. Hmm. Fine. So this is your negative feedback here. Okay. And what is the V out is equal to what? What is V out? Anyone?
G by 1 plus GH, HG.
Correct. Times V in or V ref here, right? Correct. And this is the equation of the whole closed loop system, right? From V ref to V out. Okay. Now we know that any system, for it to be stable, what is the requirement for a system to be stable? The system's transfer function, which in this case is V out by V ref, which is equal to G divided by 1 plus
Dominator should be
GH. This system transfer function. Yeah, someone was saying something. Go on.
yeah, dominator should be not exact zero, otherwise system get unstable.
No, that is not the condition. What is the exact the condition is that the places or the frequencies at which this denominator it becomes zero, this should all fall in the left half plane of the left half complex plane. I mean the frequencies along which this is plotted, this guy here, it is plotted in the complex frequency plane. Okay, so there is this is sigma, this is j omega, and your frequency is s is equal to sigma plus j omega. This is your complex frequency. Okay, complex plane along which this is evaluated. So precisely this is g of s divided by 1 plus g of s into h of s. Okay, and what do? You evaluate it at all the s at every point in this plane, and then you find out what at which frequencies, at which s, what values of s this quantity, this denominator becomes equal to 0. Okay, and those values of s, they are called poles. Okay, so poles means what? Poles means what? Where g of s times h of s becomes equal to -1. Okay, fine. And these are the poles for the system. Now the point is the thing here is that these poles should all fall in this side of the plane. Okay, and the real part of the poles should all be equal less than 0. Okay, they should not even be equal to 0. If they are equal to 0, then basically they have sustained oscillations in the system. That is not desirable. So we want all the poles should fall in the left half plane. Okay, then only we can say that the system is stable. And to check this, you understand, right? This is a very cumbersome task to take all the points in the on the complex plane and then see what happens for all those points and see where are the poles and all. So it becomes a tricky thing. So some genius Nyquist, he devised a methods to find out what to do in that situation. How do you find whether the system is stable or not? So what did he say? As someone pointed out, he said that you simply take the loop gain, okay, which in this case is g into h, and you plot it. Okay, you plot it with respect to, sorry, you evaluate it at s is equal to j omega. You evaluate it at s is equal to j omega, and then you plot it. Okay, and then you see whether it encircles the -1 comma 0 point or not. So this is again, so when you plot it with respect to s is equal to j omega, this may again be give you some this thing. This will again be in general complex. Okay, this whole quantity here may in general be complex. So you can have everything, but -1 comma 0 is the critical point here. And he said that basically this plot here should not encircle this 1 comma 0 point. It should just be it should not encircle this 1 comma 0 -1 comma 0 point in the anti-clockwise direction. If you have this encirclement in the anti-clockwise direction, then you have some poles in the right half plane, which means that the system is unstable. Okay, so from here only basically you can come up with the idea of phase margin. So I guess everyone is comfortable with these things, right? Because this was covered in much detail in the lectures. So if someone has some doubt, they can ask me. I will not be covering this. I will just be going on, assuming that everyone knows these things. Phase margin was what? It was it was basically the distance in terms of phase, in terms of degrees, which you have from the 180 degree. I mean, so okay, let's do this with another color. Okay, so the moment this plot, sorry, the place at which this plot touches this, this is the Nyquist plot. Okay, this is the plot of loop gain versus frequency, I mean j omega. Okay, so this is the plot here, and the place at which this loop gain, it becomes equal to 1. This is the place, right? This is a unit circle here, and the place where this plot here touches the unit circle at this frequency, at this place here, the magnitude of your loop gain is also equal to 1, right? I mean, this is cutting the unit circle, right? So that is why its magnitude should also be equal to 1. Magnitude should become equal to 1 here, right? Magnitude of L of j omega equal to 1 at this point, right? At the place at which this happens, you have to see what is the angle, how much is the angle from here. Okay, so this is your theta and this is your phase margin. Okay, the angle that it is remaining from this 180 degree, this is minus 180 degree, right? This angle here from here to here, and you see that it has some it has not reached minus 180 degree yet. There is some part remaining. So this is the this is the angle which is phase margin. So I guess everyone everyone understood that. Cool. So theta pm is equal to what? Is equal to pi minus tan inverse. So whatever you have, I mean phase at pi minus phase of loop gain. Okay, this is your phase margin. Cool. So there is another term called gain margin. This was not covered in the lectures, I guess. Was this covered in the lectures? Gain margin?
No.
Yeah. So this is there in the assignment. So that is why I will be discussing it. So gain margin is nothing but, so let me take a copy of this photo. This is nice one. Sorry, yeah, this is like this. Okay, so what is gain margin? Gain margin is this thing. So basically gain margin is the gain that you are having with respect to 0 dB. Okay, gain margin is the gain. So I will be, it is just the ratio, or in terms of dB it is the difference between, so I will be talking about a magnitude. Okay, so it is the ratio of the gain, ratio of, or inverse, sorry, not ratio but inverse of gain so it is not inverse but it is exactly gain or loop gain magnitude. It is the loop gain magnitude when angle of L of j omega equals pi. Basically this means that for what is gain margin is that when your loop gain, this is the loop gain plot, right? When its phase becomes equal to 180 degrees. Okay, so in this plot you see its phase becomes 180 degree only at infinite frequencies, right? But when that happens, when its phase becomes 180 degree, what is the gain at that point of what is the loop gain magnitude? So let's take another example where it can be clearly shown. Here it is difficult to show this. So if you have this, this is minus 1 comma 0 point, and let's say you have this plot. Okay, and image of this can be like this. Okay, so here you see the moment your system's phase becomes 180 degree, your loop gain phase becomes 180 degree at this point, right? At this point the loop gain plot, loop gain's phase becomes equal to 180 degrees, isn't it? This is j omega, but this is the point where your loop gain's magnitude becomes equal to 180 degrees, correct? So at this point, what is the gain of your loop? What is the loop gain magnitude? That is what is gain margin. Okay, the loop gain magnitude at this point is equal to gain margin. Okay, is that clear? I guess that explains everyone. Does anyone have any doubt here?
So loop gain at that point is 0, right?
No, at this point is not 0. How it is
It's
0?
it is in the x-axis. There is no y-axis.
Yeah, it is x-axis. But what is meant by loop gain? How is loop gain equal to 0 at this point? Loop gain is what? Loop gain at any point in this Nyquist plot. So what is loop gain magnitude? Let's say you want to find the magnitude of loop gain at this point here. What is the magnitude of loop gain here? It is equal to the vector. It is equal to the magnitude of this vector, right? The length of this vector, which is joining it from origin to this point. That is what is the magnitude, isn't it? So from at this point here, you see that the magnitude of this vector here, which is joining, the length of this vector is only less than 1. Minus 1 comma 0 point is here, but this is less than, right? Less than this.
Okay.
Correct?
It is magnitude, right?
Yeah,
it is
magnitude.
It is vector.
Yeah. Vector magnitude. Correct.
Distance from 0 to that point.
Correct. That is the loop gain magnitude. Yes. That is the magnitude of loop gain. Correct. Okay. So I guess everyone is clear on these things: gain margin, phase margin, and all. So if that is okay, then let's see what else. Fine. Move on to some questions now, since not much time is left. Okay. So these questions are very similar, I guess, to the questions that are given in the assignment. So okay. So in this question, yeah, so this question is actually op amp has a DC gain of how much? 10,000 volt per volt and two identical poles at a frequency of 1 megahertz. So it is placed in unity gain feedback configuration. Determine the unity gain frequency in megahertz. So can someone attempt? Can someone tell me what should I do about the first question? This is the first question. What should I do here? This is your op amp, okay, and let's say this is plus, this is minus.
Sir, please zoom the First, please show my screen, sir.
Okay, 1 second. Let me see. What can I do here? Can I zoom it or not? So unfortunately, I cannot zoom it here. I'm sorry. This is. I don't know how to zoom it. So I don't know how to zoom it here. So is it not visible?
Visible.
But
It's visible, but it is quite small.
Okay, 1 second. So is the question quite small or is what I'm writing quite small?
question.
No, sir, the questions.
Okay, questions are quite small. Okay, so I will tell what the question is. So let's forget about that. So question is that this op amp here. Okay, so what I'm writing, please focus on that. This is the op amp here. Okay, and this op amp has a gain which is equal to 10 to the power 4. Okay, volt per volt. Doesn't matter if you don't even write the units because it is unitless. This op amp here has the unit of 10 to the power, sorry, gain of 10 to the power 4, and it has two identical poles. Okay, it also has two identical poles at what at 1 megahertz. Okay, this op amp has two identical poles at 1 megahertz, and then it is connected in this unity feedback operation or feedback configuration. So what is meant by unity feedback? Can someone care to explain that?
V naught by K is V out by V in is equal to 1.
Correct. So in this case, V out, unity feedback configuration.
Can you please copy paste that question in chat box?
Okay, but that doesn't matter. I mean, if you want, I mean, so what this is what I'm saying, right? So you can simply understand it from here. So okay, 1 second. So I will do that. Don't worry.
Sir, are the recordings available?
Yeah, recording is available. I will be posting it. Okay, so
Like, can you please share that posting link, like YouTube link?
Yeah, I will share it after the session is recorded. Then only I post it. So
No,
after
sir.
that,
Last week's also you did not share actually, so that's why.
so that is what I said. Now I have posted it on this thing in the chat of this SWAYAM portal. There is this forum, right? In the forum I have posted it. Please join the forum. So that is beneficial for everyone. Whoever is enrolled in that course, please join the forum and be active there. If you have any doubt, post it there. I did post it. Post my YouTube lectures there. YouTube link also. So it's a whole playlist created only for this particular course. So you can subscribe to that playlist. So you will be getting that notification of every week's recording. Fine. Cool. So okay. So this is the condition, right? So what is unity feedback configuration? It means that the forum is an SWAYAM portal. SWAYAM or NPTEL, whatever you have, there you will have this forum.
Hello, sir.
Yeah.
Sir, actually, I was looking for the last session video recording. Is it available?
Yeah, that's what I already told it several times now that it is there.
Oh, I'm sorry. I'm really sorry.
Yeah, please please be attentive. Otherwise, it becomes extremely cumbersome for me to answer the same question again and again.
Yeah. I'm sorry. I'm really sorry.
Yeah. Cool. Fine. So okay, so this is what it is. Unity feedback configuration is what? V out by V in should be equal to 1. Okay. So this is in this case they have asked what is the unity gain frequency here for this particular case. You see the gain of this op amp, the DC gain of this op amp is 10 to the power 4, and it has two identical poles at 1 megahertz. So what will be the transfer function of this op amp? So what is the A of S basically? What will it be? If it has a gain,
DC gain
yeah, DC gain.
10 to
Okay.
the power 4 by
Yes.
4 by 1 plus ace by
Okay.
pi pi 2 pi
Okay.
1 meg 1 meg whole square
Good. Good.
total whole.
Yes. Yes. Good. Very good. This is the gain. Gain. This thing. This is op amp's gain. Okay. Now it is said that op amp's gain here is, this is A of S. Okay. So this is A of S and it is connected in unity feedback. So the question that they have asked is, what is the unity gain frequency? So if this is the condition, what is unity gain frequency? So before finding unity gain frequency, you have to find out what is the loop gain, right? Correct. First you have to find out what is the loop gain.
Find the transfer function over here? We
What?
just applied. How did we find the transfer function over here?
How did we find the transfer function, you are saying?
Yes, yes.
Yeah, transfer function is, it is given that it has a DC, this op amp here, it has a DC gain of 10 to the power 4, right? And also it has been said about this op amp that there are two identical poles at 1 megahertz for this particular op amp. Okay. So the DC gain of this op amp is given. Okay. And you also know how many poles it has and what are the location of these poles. So after that it is just like this, right? So this is A DC divided by 1 plus S over P, P1 into 1 plus S over P2 and so on, right? This is the this is a general this thing of transfer function. If you know all the poles of a transfer function, if you know all the zeros of the transfer function, and you also know what is the DC gain, you can write the transfer function, isn't it?
Yeah, yes, sir, I got it.
Yeah, correct. So this is what it is. This is the loop gain. Okay. Sorry, not loop gain, but this is the transfer function of this op amp. Now you also have to find out the loop gain before finding the transfer function, before finding the unity gain frequency. So tell me, how do you find the loop gain here in this particular case? What is the
Mod of ace.
What?
Mod of ace is equal to 1.
No, I am asking how do you find out? Yeah, you are saying
Okay.
the answer is correct, but how did you come to that? Why did you say that answer?
Because the gain should be 1 at that frequency. So that's why
No,
I'm
true.
considering what frequency there.
I'm asking right now, what is the loop? What is loop gain here? What is loop gain in this particular example? What is loop gain and how do you find it in this case? Loop gain. First of all, do you identify there is a loop in this system here? Do you identify some loop
Yes.
gain? Correct.
Yes, sir.
Yes.
Now, how do you find the loop gain if you identify a loop?
We'll break the loop and we will give some input at the integrator.
Correct. First of all, you have to ground the inputs. All the inputs you have to desensitize. If there will be a current source, you have to open it. If there is a voltage source somewhere in the input, then you have to short it. So what do you do first? You first take this guy here, or not copy paste it, I'll just redraw it. Okay. First of all, you ground this input, right? And then this is the place where this is your feedback, right? This was your feedback, but I will break it here. Okay, at this point. Now at this point here, I apply a V test. Okay, fine, cool. And where will I observe the what should I do after after applying V test?
We should find what is the voltage returning from.
Correct. So this is the V return, right? So what is loop gain in this case? Is V return upon V test. Okay. And this is what is we have to find out. Okay. So tell me, what is V return by V test in this case?
It's equal minus AS into VT.
Correct. No, I'm asking only the transfer function, right? So it will be only minus AS, isn't it?
Okay.
Yeah. So this is the loop gain. So what is loop gain magnet? What is? How do you find out the this thing unity gain frequency? You evaluate loop gain at j omega, right? You evaluate loop gain at j omega, then you find its magnitude, and then you equate it to what? You get equate it to 1, isn't it? So tell me what will that be here? You have to find out a of s at j omega, and then this everything you have to equate its magnitude to 1, isn't it? So as someone told earlier itself, what will you do here? The magnitude here of a of s is 10 to the power 4 divided by 1 plus 1 by, sorry, not 1 by, but j omega divided by 2 pi into 1 mega. Okay, and this is the magnitude of this will be,
Yeah.
correct?
Or a square, one more square. Okay.
No, this is I've written magnitude here, isn't it? I have not taken the
Yeah.
magnitude yet. I have just put the magnitude sign here. So what will
Okay.
it be? Magnitude 10 to the power 4 divided by 1 plus omega square divided by 2 pi, so not pi into 1 mega, the whole square,
Yes.
and then again a square.
Okay.
Not square, but sorry, this is, will be under root here, and then square. So is that clear with everyone? I've just taken the magnitude of this quantity here inside this brackets. Okay.
The above thing here is not clear, means the
The,
diagram.
this quantity. Oh, this
No, no, no.
this one.
Yes, sir. How did you find the loop gain over here?
Oh, okay. So, okay. So loop gain. How do you find the loop gain for any system? First of all, you have to identify where is the loop, right? So in this case, in this figure here, can you identify that there is some loop? There is some feedback loop.
Yes, sir. It's a negative
Yeah.
loop.
So where is that feedback loop here?
Over disconnected to the negative terminal and the output.
Correct. So it is connected in this fashion. This is the loop, right?
Yes, sir.
Yeah. So after that, what do you do? After once you identified the loop, what do you do after that? What is loop gain?
Basically, we make all the independent source off.
Yeah, correct.
And
You first desensitize the independent sources. Yes. After that,
after that we mm, put in our input in that loop.
yeah. How do you put your input in the loop? Yeah. For that only, once
We
you
force
identify.
that input. Yes, force that input into the.
Yeah. Not that way. You see, what do you do? First you identify the loop that you did. Okay. After that, you correctly said that we have to desensitize the inputs. Okay. We have to desensitize the inputs. Okay. And after that, what do? You break your loop. Okay. You break your loop somewhere. Okay. So in this case, I broke the loop at this point here. Okay. And once you break the loop, after that, there will be two terminals after that, right? Once you break something, break a closed loop, then you get two open ends, right? Clear?
Yes, sir. Yes.
Correct. Now one of that open ends, you connect it to your input voltage. Okay, whatever voltage you want to drive it with, and the other open end, you just observe what is coming back. What is the return voltage at in that open end? Okay.
Okay, sir.
Yeah. So that is what we are doing here. One of the open end here is connected with this voltage source. Okay, and we are checking what is coming back in this direction, and that return voltage we have named it as V return, V ret, and we are just checking what is V return by V test, and that is loop gain, right? That is loop gain, L of S.
Okay, sir.
Correct. So after that we did this. Fine. So after that you understood, right? So once you find the loop gain, then you have to, in order to find the unity gain frequency, you just have to equate the magnitude of the loop gain to 1, and you have to see at what frequency that holds true. Correct? So here we have equated the magnitude of this loop gain. First, loop gain is this is in Laplace transform, right? Loop gain is a function of s here, isn't it? So first we have to evaluate that loop gain for at j omega, okay, at s is equal to j omega, and then take the magnitude of that and then equate it to 1 and see at what frequency, at what omega it holds, and at the frequency at which it holds, that is the frequency, that is the unity gain frequency. Okay, okay, fine. So yeah, so this is what I have done here. So what is the answer? Can someone tell me?
100 megahertz.
How much?
100 megahertz.
Sure.
Yes, sir.
10 gigahertz.
Let's do it now. What is the hurry? 1 plus omega by 1 2 pi into 1 mega. Sorry, the whole square is equal to 1. Now, are you guys familiar with Bode plots?
Yes, sir.
Yes, sir.
Cool. So you remember in Bode plots that you remember how do you draw Bode plots? Let's talk about magnitude for once. So let's talk about L of j omega magnitude here. Okay. So we were given that it has the DC gain of 10 to the power 4. So what is what is it in dB? 10 to the power 4 in
Log
dB,
20.
it is equal
Yeah.
to what? 20 log of,
80 dB.
yeah, correct, it is 80 dB.
8.
Correct. So here it is 80, correct. And after it hits a pole, after it hits some pole here, after that it moves at 20 dB per decade slope, right? Minus 20 dB per decade. It starts to go, it start decreasing from there, right?
Yes.
Isn't it? So it's a log plot, so that is why it is like this. So after it hits a pole, its slope, it starts to decrease, and the slope at which it is decreasing, it is minus 20 dB per decade, right? So tell me that in the question it is given that this first pole, it has two repeated poles, right, at this point at 1 megahertz, right? So it has two repeated poles at this point, 1 megahertz. So what will be the slope in that case if it has two repeated poles at this
Minus
frequency?
40 dB.
Minus 40.
Correct, exactly. So it will be minus 40 dB per decade.
Sir, I have one doubt.
Yeah.
Sir, in control system, when we need actual value to dB, then we take 20 log and that value.
Yeah.
But in computation, we generally we take 10 log that value.
No, that
What?
is a different thing. That is power, and this is voltage. I mean, that is also other thing, like that is dB10. It is generally mentioned there in dB10, dB20. Okay.
Okay, sir.
Okay. Let's come to that question after some time. Okay. So let me finish this first. This is important. Anyways, so this is 1 megahertz, right? If you have repeated poles at 1 megahertz, then your slope of this will be minus 40 dB per decade, right? So in the question, it was given that you have two identical poles at 1 megahertz and you have a gain of 10 to the power 4, isn't it? Which means that you have a gain of 80 dB at this point here, DC gain of 80 dB, and after 1 megahertz, from 1 megahertz, your plot starts to decrease at the rate of minus 40 dB per decade, right? So tell me how many decades it will take for this gain here to become 0.
2 decades.
Only one.
2 decades, sir.
2 decades, exactly, because this is minus 40 dB per decade, right? and there are 8. This is 80 dB, so it will take 2 decades, isn't it? Correct. So from the Bode plot, you can directly say that basically your pole in this case, not pole but unity gain frequency. So this is the unity gain frequency, right? Omega u loop here. This will be equal to simply 100 times 1 megahertz or 100 megahertz. Is it clear? So what is 2 decade? 2 decade is simply 10 into 10, right? 2 decades. So what is 1 decade after 1 megahertz? It is 10 megahertz, and after that another decade is 10 into 10, which is 100 megahertz. So it is 100 times 1 megahertz. At that frequency you have omega u loop. So someone was saying 100 megahertz, right? So that is the correct answer. So that is so fu is 100 megahertz. Mind it that in the question, since everything is given in megahertz and all, and not mega radian per second, so you are expected to answer in hertz only, in that unit only. Okay, so if someone does this, that omega u is equal to 2 pi into 100 mega radian per second, then unfortunately they have done the right thing, but they will not get any marks for that. Okay, because in the question everything is in hertz and all, so in the same unit you are expected to answer also.
Excuse me.
Yeah.
I have one question.
Yes.
When we have written the transfer function, that just at the beginning itself, when we define it as as is equal to a of 10 raised to 4 upon 1 plus s upon 2 pi. So instead of 2 pi, can we just mention it as 1 plus s upon 1 megahertz? So 2.
I mean, yeah, you can do that, as long as, because anyway when you replace it with j into omega, okay, so this omega will be having 2 pi times
2
f.
pi
It can
f.
also be written in that manner. So 2 pi and 2 pi will cancel anyway, so it doesn't matter. But as long as you know what you're doing, it doesn't matter. But you should know what you're doing.
Okay, thank you.
Fine. So yeah, so someone was saying 100 megahertz, so 100 megahertz is the correct answer. But for that you didn't need to do all these things. You could have simply said it from your Bode plot. Okay. Fine. So now we have to find the phase at 1 megahertz in degrees. So 1 second, let me turn on the lights, and it's getting kind of dark in here. Yeah, so we have to find out what is the phase at 1 megahertz in degrees. Second question. So again, so does anyone know about this Bode plot, how to plot phases? So this was the magnitude part of Bode plot. So how do you plot phase response in Bode plots? How do you draw that? Can anyone tell me?
A different value of omega and angle.
Yeah, that is true. That is the definition of Bode plot. But I am asking, how do you plot it? I mean, Bode plots, how do you do? In Bode plot, how do you show the phase response?
We will take, like, whatever pole is there, we will take lower value and higher value. And then we will, no, omega, let's pole is omega p.
Okay.
So we will take the nearby point omega by 10 and higher point 10 times of omega p.
Correct.
And approximately we will draw the lines.
Correct. Fine. Exactly. So this is what exactly is done. So let's say again in the same question. So now I'll plot both the magnitude and the phase. Okay. So let's say this is your 20 log 10 of magnitude of L of j omega. Okay. This is omega. Cool. And the same plot here, I will be plotting the phase. Sorry. Okay, so let's say this is your pole omega p. Okay, and let's say it is only one pole. Okay, now let's say at DC there is some gain. So the moment this hits this first pole, after that it starts to go down, isn't it? At the rate minus 20 dB per decade, correct? And when it reaches this 0 dB point, this is 0 dB. Okay, at this frequency we say this is omega u loop, correct? Fine. Now the same plot, let's do this phase response. Omega again. Now this is omega p. Okay, what in the Bode approximation, what do? We select points omega p by 10 and then omega p into 10, and then what do we do? We say that okay, this starts at this frequency. Okay, so let's say this is 0. Okay, in phase, this is the 0 degree phase. Okay, let's say this is 0 degree. So initially when nothing happened, initially at very low frequency, your pole your loop gain angle is 0 degrees. Okay, and after that when the first pole hits, when the pole hits here, your magnitude of loop your phase of loop your this thing phase of loop gain, it becomes equal to what? Minus 45 degrees. Okay, and after approximately 10 times of this frequency, of the pole frequency, you say that
It will become minus 90 degrees.
correct, you say that it reaches minus 90 degree after this approximately. And this is drawn very smoothly, but Bode approximation says that you draw a straight line till this frequency omega p by 10. From omega p by 10 to another this thing, you draw a straight line here. Okay, so that it crosses this minus 45 degree here, and after this frequency you again make it 90 degrees here. Okay, so this is the Bode approximation. Okay, fine. Now
Sir, can you elaborate this concept, multiply divided by 10 and multiply by 10?
It's nothing. I mean, you see at omega p, when there is only one pole in the system, so this is the system's response. Let's say L of s is some k divided by 1 plus s by omega p. Okay, this is your L of s, right? Now what is L of j omega? This is k by 1 plus j omega by omega p, isn't it? So what is magnitude of L of j omega? This is k by 1 plus omega square by omega p square under root, isn't it? And what is phase of L of j omega? This is equal to minus tan inverse omega by omega p, correct?
Yes, sir.
Correct. So what I am saying is that you see that when omega is much smaller than omega p, then tan inverse is tan inverse of a very small quantity. What it is? Very small quantity. Let's say what is tan inverse 0?
0.
Correct. So let's say if it is very small, not 0 but very small, then you can approximate it again as 0 only, right? Please mute yourself, whoever is. Yeah, I mean the person who is asking can unmute themselves, but remaining everyone else, please mute themselves. This creates some noise in the classroom. Fine. Yeah, so if the if omega is much smaller than the pole, right? If the frequency at which you are calculating the angle of L of j omega, if that is very smaller than the pole frequency, then you can still say that the angle is 0 only, right? Tan inverse of that tan inverse omega by omega p, is approximately equal to 0 if omega is much smaller than omega p, right? Fine. Now what Bode stated was that he said that please do not make I mean this approximation much less is for is like it leaves ambiguity, right? Some for someone much smaller can be 10 times smaller, or for someone it can be 100 times smaller. It leaves ambiguity, right? So what he said that much smaller is equal to 10 times lesser. That is what he said. So till for frequencies, if omega is less than omega p by 10, then you can say that tan inverse of omega by omega p is equal to 0. That is what he said. Okay, so that is why
Yeah.
we have this omega p by 10. So it starts with 0 here and stays 0 till omega p by 10. Okay, fine. Now tell me what is tan inverse of 1?
45.
45 degrees, exactly. It is 45 degrees. So that is why minus tan inverse of omega by omega p, when omega is equal to omega p, what will it be? When omega is equal to omega p, what is minus tan inverse omega by omega p?
Minus 45.
Minus 45 degrees. So that is why starting from omega p by 10 here, you start going down, because you say because Bode said that till omega p by 10 we can say safely that we can assume that it is equal to 0. The angle is 0. It is very small, so it is 0. Okay, but after that he said that now the angle will start to go down, and exactly at omega p we see that the angle should become minus 45 degrees. There is no approximation involved here, right? Please mind that in this writing this here, there is no approximation. This tan inverse of means at omega p, the loop gain phase is exactly equal to minus 45 degrees. There is no approximation here. Approximation was here, okay, and at these frequencies, but there is no approximation here. It is exactly equal to minus 45 degrees. Is that clear?
Yes, sir.
Fine.
Is it valid only for a single pole system?
Yeah, so this is what I'm saying is right now for single pole system, okay, but the same concept is applied everywhere, so that I will be talking now. But yeah, so telling that after that, so now what is tan inverse of infinity?
90 degree, 90 degree.
Correct,
90.
90 degree of pi by 2, anything. Correct. Now let's say I do not have infinity but very large number, okay, tan inverse of very large number, that is also approximately equal to 90 degrees, right?
Yes.
Now again this leaves ambiguity, right? Because for someone very large can be 100, for someone very large can be just 10, so for someone very large can be 1000 or anything. So what Bode again did is that he said that no, please do not leave any ambiguity here, we just assume that very large means 10. Okay, so once this omega by omega p, if it exceeds 10, then we say that tan inverse of omega by omega p equals 90 degrees. Okay, so that is why there is these there are these values here, omega p by 10, omega p and omega p into 10. Okay, after omega p into 10 it becomes minus 90 degrees here. Is that clear?
Yes, sir.
Cool. So this is how you plot the phase response. Okay, now if in your system instead of having one pole here you have two poles here, I mean repeated poles at this point, then what will happen? So as you said earlier, you said that we have this 40 dB per decade slope here, right? In this case we have this 40 dB per decade slope, correct? Now in the phase response what should happen, tell me?
My omega p goes into minus 180 degree.
Correct, it will go to, sorry, let me pull it down. So it will go to Yeah, and how should it go to minus 180?
Cut it by minus
Minus
90 degree.
90, then minus 180.
Correct. So what it does is that at again the same thing. The approximations have not changed. You start your till omega p by 10. You say that again it is 0 only. Nothing has changed. But suddenly from omega p by 10, now since rather than going like this, or sorry, like this, it will go in this direction. It will go like this. Okay. At omega p, it should become 90 degrees, isn't it? 45 degrees was due to one pole, but since there are repeated poles at this frequency now, so it should become double of that, isn't it? So is there any doubt in that statement? If you had this tan inverse omega by omega p.
Hello.
Yeah, hello.
Sir, actually, I got doubt in sir the question number six, sir, from assignment third.
Yeah, I cannot discuss that. I'm sorry. I cannot
Sir, I
discuss.
just want to know the way. Sir, actually, I'm not getting how to.
Please, I cannot discuss that. I mean, please focus this. I mean, this question is very similar to that. So because when you do this, you will be able to do that also. Okay.
Okay, sir.
Yeah. Please pay attention to this one so that you will be able to solve that also. Fine. So yeah. So I was saying that yeah. So when you had only one pole, then your phase reached minus 45 degree at that pole frequency, right? Now when you have two poles, your phase should reach minus 90 degrees. It's just 45 into 2. Okay. I don't think anyone should have any doubt there. Okay. When you have repeated poles, then it simply becomes equal to 2 times. Okay. Fine. So this becomes 90 degree at this point, and again after 10 times of that frequency it reaches minus 180 degrees, and from there it becomes constant. Okay. So this is what is Bode approximation in phase. So coming back to the same question again, what is the phase at 1 megahertz? So we remember that, calculate the phase at 1 megahertz. So 1 megahertz we have two poles, right? Two repeated poles. So what should be the phase at 1 megahertz?
Minus 90.
Correct. It should be minus 90. This is the simple question, right? So that's all. In this question, you have to find out what is the phase at 1 megahertz, and that is equal to minus 90. Fine.
Is this concept valid for more than two pole?
What concept? I mean, if the
Phase concept.
no, this phase is simple, right? I mean, this is how to draw body plots. So
More than if I use this concept for more than one pole.
I did use that this concept for more than one pole, right? There are two poles in this system, so that it started from 0 and went to minus 180 degrees.
Both are at same point, no?
Yeah, both are at same point. Yes.
If both are different, then
Yeah,
because
then you have to then you have some other ways, right? But I will not be covering that because I asked and people said that Bode plots, they are comfortable with Bode plots.
because I am thinking that you assume that for we have to assume large omega p at 10 OWP, 10 omega p.
Yeah.
In that case, if I have 0.2 and 6, then in that case our 10 omega p is greater than 6.
Yeah, I understand. So in that case, you see, you plot Bode plots individually for each this thing, each poles, okay, and then you add them. That is how Bode plots are done. So if you want, you can refer. 1 second. So I will pass you a link. Okay. So you can look at that. This is a nice link. You can. Sorry. I will this yeah, so in the chat box I just posted one very nice link to as a guide to plot Bode plots. So you can refer that if you have any doubts. Right now I do not have much time to deal, to go into much depth. Okay,
Okay, sir.
fine.
Thank you,
So
sir.
now, yeah, welcome. So now we have to find the phase margin. Okay, so now we have to find the phase margin. So how do you find the phase margin? So in this case we have L of S is equal to A of S minus A of S, which is equal to 10 to the power 4 divided by 1 plus S by 2. Let's remove 2 pi now. Everything is in, assume that everything is in frequency only, F, and in hertz only, is 1 megahertz, right? And this is your and square of this. So this is your L of S. So what is the phase margin? What is meant by phase margin?
The system behave as a negative feedback.
Yeah, so phase margin is actually the angle between the difference between pi and the angle of L of j omega, right? At omega u loop. This is phase margin. So what was omega u loop here? This was 100 megahertz, right?
Yes, sir.
Correct. So omega u loop is equal to 100 megahertz. Cool. So, and what is the angle at 100 megahertz? What can you say from this approximation here?
It will be approximately 90 degrees.
It will be approximately 90.
Minus 180, no?
Correct.
Minus
It will be
180.
approximately 180 minus 180 degrees exactly. Right. So okay. So this is not pi minus. This is pi plus. Okay. This is pi plus. Okay. Fine. So the angle of L of j omega at omega u loop will be approximately equal to what? 180 degrees. So phase margin approximately will be equal to 0 degrees, isn't it? Anyone has any doubt in that?
So it's 180 plus minus of 180, right? That's why it is 0.
Yeah, yeah. That is what I have written here, isn't it? 180
Okay.
plus minus 180 here.
Yeah, okay.
Okay, so okay, let me elaborate it. Okay, phase margin here is equal to pi plus, so pi is equal to 180 degrees here. Okay, plus minus 180 degrees. That is why it is equal to 0 degrees. Approximately. It is not exactly, it is approximately. Okay. So if you want to find the exact phase margin, then what you have to do? 180 plus angle of L of j omega, which is what? It is tan inverse of,
Minus
yeah, minus tan
minus
inverse
10.
of what?
100 meg by
100 megahertz, not 100
by 10.
megahertz, right? It is, yeah, sorry, it is 100 megahertz divided by what?
10.
1 mega.
1
Oh,
mega.
1 meg.
1 megahertz.
And
Okay.
then there will be a factor of
2
2
times.
here,
Yeah, 2 times.
correct? So you can find it, it will be approximately equal to 178 something degrees, very very close to 0 degree phase margin. Sorry, this will be approximately equal to 2 degrees or so. Okay, very close to 0 degree. So it is extremely close to unstable system. Okay, now there is another question, which is you want to, now suppose you want to move one pole, okay, one pole of the system to a very low frequency. So you can see that from in this case that phase margin is extremely poor, right? We want in a well-behaved system, as was also explained in the week's lecture. For a well-behaved system, we want the phase margin to be somewhere around 76 degrees, right? For a well-behaved system, for a well-behaved system, phase margin should be approximately 76 degrees, right? I mean, in
Yes.
this case, your system will be critically damped. There will be no overshoot. Okay, it will be critically damped. So, so for that we need 76 degree phase margin. But you see that in this case the phase margin is very very poor. It is 2 degrees or that is very close to 0 degrees, and it is very close to being unstable. So we do not want that. We want to make our system stable, right? We want to improve our phase margin. So what do we do? So that is the question. Now we want one pole to we want to move one pole to a very low frequency, okay, so that the op amp has a phase margin of 45 degrees in unity feedback configuration. So what do we want? Right now the situation is like this, that we have this gain here 10 to the power 4, and then we have suddenly two poles appearing here, and then it starts going at 40 dB per decade, minus 40 dB per decade, okay, and this is your omega u loop. So but because of this your system has become unstable, approximate, very close to become unstable. Now what do we want? We want to move one pole very close to very low frequency, okay. You want to move one pole to a very low frequency such that your system starts doing this. It starts to go at a minus 20 dB per decade slope here, okay. Okay, so how do I show that here? We want to do this. So let's say your one pole is at a very low frequency, okay, at a very low frequency, such that from here only it starts to move at minus 20 dB per decade, okay, and it does something like this, and from here it starts to move at minus 40 dB per decade, or yeah, it does something like this. So in that case you see that at this point it will have a good phase margin, okay. So that is what the question is. So
Sir,
what?
can you repeat it?
Yeah. So what I'm saying is, at right now what was happening is that your system had this large gain, right, at DC, and this gain was continuing till it hit both the frequencies, two poles. There were two
Yes.
repeated poles, right, 1 megahertz. So
Yes,
after
sir.
that,
Omega U loop is unity gain frequency.
correct,
The
omega
same
loop
thing.
is a unity gain frequency, yes. Yeah, so at this omega p, you have two omega p's in repeated poles here, and then the system started going down with this minus 40 dB per decade slope, and you saw that in this case phase margin became very poor. It was 2 degrees, right? Now
Yes.
now we want to improve the phase margin of the system. How do we do that? We introduce a very strong pole, right, very powerful pole in the system at a very low frequency, okay, such that it starts going down at minus 20 dB per decade here itself, from this frequency only, omega p1, okay. Now it will start to go down, and
So in this case, omega U loop will be changed or it will
correct,
be
it will
this?
be different. So it is omega u loop is here in this case, okay, somewhere here. I mean, it is at a different point, that's all. Now we have to find out where it should be, okay. So let's see how to do that.
Sir, excuse sir.
Yeah.
Sir, can we do the same thing by shifting the pole to the higher frequency so that we can use op-amp in higher frequencies also, rather than shifting in
No,
towards lower
the point
frequencies?
is you have to make the system stable, right? So all those things will be clear. A lot of things, lot of design consideration will be explained in the next week 4 content, okay. So hold on for that. But yeah, so there are many things which can be done, but at this point, let's say we just want to make our system stable, compensate it, okay. I mean, this is 2 degree phase margin, it's nothing, right? It's not a very good system. For a well behaved system, we need 76 degree phase margin. So how do we do that? One of the ways to do that is to make sure that we have a very strong, powerful pole at a very low frequency, okay, and all the other poles are at a very high frequency compared to that. So that is what is done here. We have introduced a very powerful pole at a very low frequency, omega p1, okay, and because of this, once the system hits this pole, it starts going down by minus 20 dB per decade, okay, and what do we want? We want a phase margin of 45 degrees in this case, okay, by shifting. So we have two poles in this system, right? But both the poles in the system were initially at 1 megahertz only, at the same place. We have two poles at the same frequency. But now what do we want? We want one of the poles to go to very low frequency. One pole to very low frequency.
Sir, why is it 45 only and no other value?
No, this is just in the question, okay? This is just given the question. I just framed the question like that. Just 45 degrees. You can have
All
any,
right.
yeah, you can have any other value. Doesn't matter. Okay. Yeah, we want a phase margin of 45 degrees by shifting one pole to very low frequency. The other pole is still at 1 megahertz only. Okay. So what do we do in this case? How do we proceed? So the question is, find the omega u loop, new omega u loop, sorry, new fu or unity gain frequency, and the location of the first pole. So we have to find out what is location of this omega p1, okay, and what is the new omega u loop, such that the system has a phase margin of 45 degrees. So what do we do?
So we can find the transfer function of this.
Correct. First we have to find the transfer function. So this is a of s is equal to 2 to the power 4 1 plus s by p1 into 1 plus s by p2, right? We know that p2 is equal to what? 1 megahertz.
1 minute.
1 megahertz.
But we do not know what is p1, right? Now we have to make some approximations here. Otherwise your life will become very uncomfortable dealing with a lot of equations. So the approximation here is that this p1 is extremely low compared to p2, okay? Moreover, this p1 will be very low compared to your omega u loop also, okay? So this is approximation here. So we have made an approximation here. What is the approximation? P1 is much less than P2, and P1 is also much less than omega u loop, which is the new omega u loop, okay? And you will see that this is a justified approximation. We will just see in shortly. So when that happens, when we make that approximation, what is the one information that we are given in the question? We are given that phase margin is equal to 45 degrees, right? Correct? And phase margin is calculated where? It is calculated at omega u loop, right?
Yes, sir.
So what is phase margin? If we have assumed that one of the poles is extremely dominant here, right? One of the pole is very far back compared to omega u loop. So around omega u loop, the phase lag introduced due to this omega p1 will be equal to what? Okay, so that was a lot of information, a lot of questions asked in just a very small amount of time. So this is a of j omega, right? 10 to the power 4 divided by 1 plus j omega divided by p1 into 1 plus j omega divided by p2, correct? So what is angle of a of j omega? Sorry, and what is L of j omega? It's just minus a of j omega, isn't it? So what is this? What is the angle of this?
Minus tan inverse of omega by P1 minus tan inverse of omega by P2.
Correct, minus tan inverse omega by P1 minus tan inverse omega by P2, correct? Now what do we want to do? We want to find L of j omega at omega u loop, correct? And I have already assumed that omega u loop is much greater than P1, right? isn't it? This I have already
Yes, sir.
assumed here, approximation here. P1 is very less than omega u loop. Correct. So at omega u loop, what should be this term approximately?
90 degrees.
Correct. This is approximately 90 degrees. Because this quantity omega u loop divided by P1 will be much greater than 1, right? So this is approximately 90 degrees. And this we do not know, right? This we do not know. This we have not assumed anything about. So this should be equal to what? Sorry, this is L of j omega. And what is phase margin again? Phase margin is equal to what? 180 degrees plus minus 90 degrees minus tan inverse omega by P2. And this should be equal to what? 45 degrees. Isn't it?
Yes, sir.
So from here what will we have? 90 degrees minus tan inverse of omega u loop by P2 should be equal to 45 degrees. This will becomes equal to so tan inverse of omega u loop by P2 should be equal to what? 45 degrees. Correct. So your omega u loop is equal to what then?
P2s.
P2, isn't it? So here P2 is exactly equal to omega u loop. So basically your loop gain, unity gain frequency is equal to what? 1 megahertz only, right? So this is clear.
Yes, sir.
Correct. Now we have to find out what is the first pole location. Now we have already find out what is FU, correct? Now we have to find out omega, sorry, we have to find out P1. Okay, so how do we do that?
The gain is unity at the omega u.
Correct, exactly. So fine, so this is the gain L of j omega, no, yeah, L of j omega, magnitude is equal to 1 at omega u loop, correct? So what is L of j omega? 10 to the power 4 divided by 1 plus s over p, sorry, j omega, or I'm just finding the magnitude, right? So it will be 1 plus omega square upon omega u loop square upon P1 into, we have this another term is 1 plus omega u loop square upon P2, right? And whole under root, and this is
So
equal to 1.
P1 square and P2 square.
Yeah, sorry, yes, right, thank you. This is the one, right? Now you can again solve this, but it will be extremely cumbersome. So again you can approximate it here by using Bode approximation, right? So remember this, I have already assumed that P1 is extremely, omega P1 is extremely low compared to this omega u loop, right? Isn't it? And we remember from Bode approximation that after this omega P1, this goes down by 20 dB per decade with this slope, right? So at this point it was what, 80 dB, right? This is 80 dB at this point at omega P1, and at omega u loop its gain is 0. So how many decades it should take for from omega P1 to omega u loop to get its gain down from 80 dB to 0? How many decades should take? Yeah,
4. 4.
correct, exactly. So from here you can directly say that omega P1 is equal to omega u loop by 10 to the power 4. From here you can directly make that statement, and that is approximately fine only. Okay, so from here, from Bode's approximation,
Sir,
yeah,
or in this formula, omega u loop is equal to P2, right, sir?
Yeah, it is P2. Yes.
So that second term in the denominator will become 2, right?
Yeah, yeah, true. I mean, even after that, you will be. It will be. I mean, this compared to this, the Bode approximation is much simpler, right? You just had to look at this Bode plot, and you directly said that okay, the omega u loop, omega p1 will be just 10 to the power 4 times lesser than omega p1, omega u loop, right? You still
Okay,
have
sir.
to do
Okay.
a lot of mathematics here, right? But compared to that, that was just a piece of cake, isn't it?
Okay, sir.
Yeah. So from Bode's approximation, omega p1 is just what, omega u loop by 10 to the power 4, isn't it? So that we have omega p1 is equal to what, 2 pi into, this is this was what, omega u loop is equal to p2, right? So p2 is what, 1 megahertz divided by 10 to the power 4. So this is omega p1. So everybody understood that this question?
So how did you write 80 dB?
Oh, what is 10 to the power 4 in dB?
Okay.
It is 20 log to the base 10, 10 to the power 4. So it is equal to 80 dB.
Okay.
Correct. So everybody understood this question, right? So be mindful of the fact that we have made some approximations here. We have made a lot of this thing, lot of approximations, lot of Bode approximations, right? So please make sure you understood this. You watch this lecture again and try to understand what we did and why we did that. This Bode approximation thing, it will help you in solving your assignment in the third assignment. Okay. This is the one question that I wanted to
Sir,
discuss. Yeah, fine.
excuse
So
me, sir. I have a doubt.
yeah.
If we have three poles, how will find the phase margin? Like you consider the P1 like omega, sorry, omega in loop by P1 is equal to 90 degree. But if you have two poles, what will I write here?
No, you do the same thing once again, right? So I mean, you understood what we did. The main formula is this one
Yeah,
here. The main formula is this one here. You have how, doesn't matter how many poles you have. You just keep adding all of those phases together, right? Tan inverse omega by p1, tan inverse omega by p2 plus tan inverse omega by p3, like this. And you just have to, you just see whether you can make some assumption regarding the location of these poles, so that one term reduces to 0 or 90 degrees or so on. You just see whether you can do that or not. Many a times what you can do is that you assume something, okay, you assume that okay, let's say that this is much smaller than that, and after calculation just see whether that assumption is justified or not. So here you see, here we assume that omega p1 was much smaller than omega u loop, right? And you can see clearly see that omega p1 is indeed much smaller, like it is 10 to the power 4 times smaller than omega u loop. So our assumption is indeed justified, isn't it? So
yes.
these approximations you will learn by solving these assignments. Okay, a very important part of being an engineer. You have to assume a lot of things to make your life simpler. Okay.
Sir, what the round up to the nearest hertz?
Yeah, everything is given in the question, right? Everything is given in the assignment, right?
No,
Round up to,
no, nearest hertz. Hertz.
yeah, nearest
Round up to
hertz.
the.
I mean,
What does it mean?
if the question, if the answer is like 14.6 hertz, then you have to round it to the nearest hertz, which is 17 hertz, right? If the answer comes out to be 14.4 hertz, then the nearest hertz will be 14 hertz.
Okay.
That is all. Okay. So I guess time is up, right? 11 minutes past 6. So
Just
thank you guys.
one,
Yeah.
just one last question. Now here DC gain was given, right? If
Yeah.
I'm not wrong. Huh. And if the DC open, the loop gain is given, let's take. So still, because then loop gain will be G of G and H, right?
Right, right.
So while making the transfer function that which you have already taken it as 10 raised to 4 in this case now at the numerator.
Yes.
So then in that case, if it is a DC loop gain, then we have to take it as mm, ex- what exactly the change will be there. That is what.
Yeah, so you see, I mean, the in this case it was easy, right? It was simply unity gain feedback.
Yeah.
So let's say
Yeah.
if this was not a unity gain feedback, if it was like this, let's say it was something of this kind, not unity gain feedback, but some ratio here.
Hmm.
Okay, k minus 1 times r, and this is r. So this is not a unity gain feedback now. Okay,
Yeah.
and let's say
Okay.
you are just given this a of s. You are given
Oh.
this 10 to the power 4 DC gain here. The
Okay.
overall loop gain will be what? It will be 10 to the power 4. It will be a of s divided by k, isn't it? As we
Yes.
did
Yes.
earlier. And all the
Yes.
information that you need to calculate L of s will be most probably given in the question. Otherwise, I mean, question will not be solvable otherwise, right?
Okay. Okay. Thank you.
Yeah, yeah,
Thank you so
yeah,
much.
yeah.
Excuse me, sir. So regarding the assignment 1 and 2, there are two things to be
Yeah.
clarified. One is the rounding is not taken properly. So answer is 22.17. So what has made is wrong, and answer is given is 22.2. So
Yeah, so 21.17 is rounded off to the nearest integer, right? 22. I mean, if they want you to round off to something, they will probably mention it in the question also to round it off to that particular precision.
so
I mean, it is,
is it
everything is
mentioned
written,
anywhere?
everything is
Is it
indeed.
mentioned anywhere?
Yeah, it is given in the assignments also. Like in the assignments, it is already mentioned that you have to round it off to certain integers. So one second.
And another that is how that is for ideal current or any source, how the power delivered by any ideal source can be negative.
It can be, isn't it? It is indeed. If the power taken is negative, it means what? It means the it is delivering power, not taking power.
That is a question actually. Means we should mention only the value. That is how much power will be delivered to that. So
Yeah, if the power delivered is negative, it means that it is not delivering power. It is taking power. It is dissipating power. So in the I guess assignment solutions are also shared. Are they
actually,
shared or not?
No,
yeah,
not sure.
So
not
Yeah,
Devina,
yeah, yeah. It's shared.
yeah.
Yes.
So
Yes.
you
The answers are given.
yeah. So if you have any doubt after, so this week I unfortunately I couldn't give time for that. Next week session I will definitely take all the questions on assignment. Okay, assignment 1 and 2. If you have any doubt, so since the time is up,
Okay.
so forgive me for that.
Any chance we can get in touch with you for
Yeah,
any
you.
anything?
That is
If
one. I already said in the last session also. You can post your questions on the forum. Okay, and that is a place where you have to where you should actually ask your questions because it will benefit all of you, right? It may happen that the question that you are asking, someone else also might have the same doubt, so that it will help everyone. So please post your questions on the forum so that we can have a discussion there.
Sir, should the frequency be in integers or decimals? How the frequency is usually calculated? Whether it's calculated in integers or what?
No, it is
Or
how
even
it is up to the this thing. It is up to the requirement what we want. So
okay,
it is up to the requirement to the precision that you want, that you require.
okay, okay.
There's no hard and fast rule for that. Okay, so cool. So let's end it here. Okay, thank you for coming today. Let's see you in the next session again on Sunday, coming Sunday, right? Fine. Thank you very much.
Thank you, sir. Thank you.
Thank you, sir.
Thank you.